So, welcome to video class 21, that is stability of analysis of control system, and the stability that we are dealing with this in this module or in this class is also on absolute stability part 2. So in part 1 we have seen a method by which you can have you can have a knowledge about the absolute stability of a system. Now, what do you mean by absolute stability? By absolute stability, it refers to a quantitative analysis. It just give you an answer whether yes or no, and the theory behind that is just to find out the number of poles residing on the right half of a plane, which actually causes an instability. Okay, so that can be found out by applying a Routh-Hurwitz criterion. And why do you need to apply Routh-Hurwitz criterion? Means if you have a characteristic equation of very high order, say orders of 5, 6, 7, 8, and etc., then it will not be easy to factorize that. It will not be easy to find solution. So without knowing the exact location of the roots, we can ascertain whether there are any roots in the right half by applying a criterion called as Routh-Hurwitz criterion. And in this video we have actually did two examples. In the first example was a normal example where we have seen that I told you that there is a first step for this. Okay, so the preliminary test, and in the preliminary test you need to look at the P of S, or the characteristic polynomial. Two things are to be noted. One is no missing terms in between, and all the coefficients has to be positive. So I told you, again I'm emphasizing that point, because of this fact it doesn't mean that this particular polynomial has all its roots on the left half. Okay, so you need to do this RH criterion, but you can say a statement in the reverse order, that is a polynomial which is having all the poles in the left half of the S-plane will be having no missing terms and will be having all its coefficient positive, but the reverse or the converse is not true. Okay, need not be true. Converse need not be true. And in this example we have seen that you need to, what is that criterion? So after developing the Routh array by applying Hurwitz determinant, you can apply that that criterion, and the criterion states that look at the first column, and in the first column find out the number of sign changes between the consecutive elements. Okay, now in this example the number of sign changes is equal to 0, and we have also done a classwork for you, and you have all done it. And in this case, in this example, you have found out the answer to be an unstable system, right? So even if now when we have a first preliminary observation to this, we see that no terms are missing and all the coefficients are positive. So you are expecting a stable system, but when you found out that this is an unstable system, meaning that this particular system is having two poles residing at the right half, because this is having two sign changes you have already done. And in the last last interactive session, we have also seen I have just made you to do another polynomial where you got stuck at a point when one of the elements of the first column, first column becomes 0, right? And there are several such type of cases. So those cases can be treated as the special cases. And in this video, we will be dealing with such special cases. Okay, special cases. Okay, now case 1. So this is case 1, special case 1. That is where a 0 element is in the first column. So for that, consider, I'm just doing a problem, consider a P of S, okay, which is given by S raised to 4 plus S cube plus 2s square plus 2s plus 5. Okay, so this is a polynomial characteristic. A characteristic polynomial is given this, and you're asked to find out the ascertain the stability of the system. The stability of the system. Okay, so our primary investigation or the primary or a preliminary test suggests that no terms missing, right? No terms missing, and the coefficients, all the coefficients are positive, and this again proves that this problem again proves that the converse is not true because it satisfies these two conditions. This doesn't mean that the roots of this will always have to lie on the left half. So I tell you once again, all those polynomials with the left half poles, with only left half poles, will satisfy this condition, but the reverse is not true. Okay, so I just repeat because of its importance. Okay, now that means you can have the characteristic equation as s raised to 4 plus s cubed plus 2s square plus 2s plus 5 is equal to 0. Okay, now how to develop this root array? That's the first step, right? So in step 1, what you do is you are developing the root array. So let's start to do root array s cube, s square, s and 5, and s raised to 0, s raised to 1. Now in the first two columns, the first two rows has to be filled directly from the equation, right? So in your s raised to 4, the first element has to be 1, the coefficient is 1, then n minus 2, then it is 2, then comes 5, right? So this is s raised, this is n. If n is equal to 4, then n minus 2 is 2, then n minus 4 is 5, or s raised to 0. Then coming to s cube, then the n is equal to 3, so the coefficient is again 1, then the next coefficient is 2, and the rest is 0. Now how to find out s2? Keeping this as the base elements, from the upper two rows you need to find out the elements of s square, right? Now when you find out this, I'll just do it for you. When you do s square, what you get is 2 into, you need to do multiplication in this way. 2 into 1 minus 2 into 1 divided by 1, which is equal to 0. So the first element becomes 0, right? This is the problem. Now in this case, now you can just proceed in this way. The next element will be 5 minus 0, right? 5 minus 0. So 5 minus 0 by 5, so you are going to get 5, and the rest is 0. Now what is the problem? This is the problem. This one is the problem. Okay, and this will be a problem when you are going to find out s raised to 1. So you cannot, so you need to divide this by, right, 2 into 0 by minus 5 by 0. So that becomes infinity. So what you need to do is, now just listen. So in this case, this raw element has to be found out. Now how to find out that? Instead of 0, listen very carefully, instead of 0, you put an element called as epsilon. Okay, and the nature of epsilon is, it is the smallest number you can imagine. Smallest number, positive number, smallest positive number you can imagine. Okay, the smallest positive number you can imagine, but it is greater than 0. Just greater than 0. That means it is greater than 0.0000000. How many zeros you may put? No, don't mind. So still this is less than. This epsilon is less than this number. But this epsilon, anyway, epsilon is a greater than, is a smallest positive. This is very important. Smallest positive number that you can imagine, but it is greater than 0. So since it is positive number, it should be greater than 0. You don't need to specify that. So if I assume this as epsilon, then how will this be? Now if I'm assuming this to be epsilon, what will be the next term? Now the next term will be, how will you find out epsilon? So you know what is epsilon. Epsilon is a smallest quantity, that is, this epsilon is almost tending to 0, right? Is almost tending to 0. So what will be the value, the first element of s raised to 1? It will be 2 epsilon minus 5 divided by epsilon, right? Then next one is 0 into 0, so this will be 0, 0, right? So you got that. Now, what will be the next term? So call this as, okay, now you can call this as P. Say call this as some P or Q. Okay, let's call this as Q. This whole element as Q. So what will be the next term? The next term will be, if you want to find out the element of s raised to 0, you must use this. So 5q, this will be 5q minus 0 divided by q, or this q and q get cancelled, you will get 0, and the rest will be 0, right? So hope you understood till this much. Now the next is to apply what? Apply this what we call as the Routh-Hurwitz criterion. And what does that criterion says? In the Routh-Hurwitz criterion, you need to note down the first column, right? You need to note down the first column and check for any sign changes. Between these, no sign change. Between this, no sign change, because epsilon is assumed to be a smallest positive number. You can imagine that is a positive number, so there is no sign change. What about this? What about this? That's what we are going to find out. Okay, now let us see the sign of this 2 epsilon minus 5 divided by epsilon, right? What will be this? So you can apply the limit epsilon tends to 0. Okay, so for this, if you want to apply this limit, you can have a epsilon outside. So this will be epsilon. Okay, so you will get this as 2 minus 5 by epsilon. Okay, you don't have to do that anyway. So 2 epsilon minus 5. Now we know that say this is the smallest number, this is the smallest number. So anyway, it is smaller than 5. So this quantity is going to be a negative quantity, right? Because this is the smallest number, this smallest number minus a 5 will have to be this. This will be a negative value. That means you have a negative value here. So a negative, then a negative to a positive. So how many sign changes? The number of sign changes is equal to sign changes is equal to 2. So what's the meaning of that? The number of sign changes is equal to 2 means there are this much right half poles is there, or this 2 poles is actually aiding or it's actually causing the system to be an unstable system. So this is an unstable system. This is an unstable system. So again, proving the term which I told you, the converse is not true. So it actually, this polynomial satisfies these two conditions, but this is not true that its roots lies, some of this roots lies on the right half pole. Okay. Okay, now case 2, where all elements in a row is 0. So in that case, again, you consider the P of S, a characteristic polynomial, which is s raised to 4 plus 3s cubed plus 6s squared plus 12s plus 8. Again, the preliminary test is satisfied, right? No positive, no negative coefficients and no missings. But you cannot come to a conclusion H. So you need to find out the row. So let us just try to start like this: s raised to 4, s cube and s square. And now what is s raised to 4? So I will be writing later the rest. So this will be write the first 2 rows from the equation. So the first column, first row will be, the first element of the will be of the first row will be 1, then comes 6, then comes 8, 1, 6, 8, and the second one is 3, right, and then 12, and then comes 0. So what is yours? S2 now. S2 is going to be, right, S2 is actually what? So this will be 3 into 6 minus 3 into 6, that is 18 minus 12 by 3, or 6 by 3, or that is equal to 2, right, 2. And what about the next one? Next one will be 3 into 8, 24 by 3, which is actually 8, right? So 8, then comes 0, right? Now let us try to find out S1. Now, when you have to find out this S1, what you get is, you can see that 2 into 12, 24, minus 24 by 2, which is 0. Take the next term, 2 into 0, 3 into 0. All the terms become 0. No, you cannot use your here epsilon because this term is also 0. Right? So there is no chance of finding out s raised to 0. So now how to find out, that is the next question. How to find out this s raised to 0? That's the next question, and this is a very important aspect. Okay, so when you find that uh, s raised to 0, you cannot find s raised to 0 because here all the row elements are equal to 0. All the row elements is equal to 0. That's a problem. Now how to do this? When you see that, when you okay, now from this you can come to a conclusion that this is not going to be an absolutely stable system. Okay, this is not going to be an absolutely stable system anyway. It is not an absolutely stable system. Some problem is there if such a cases happen. So we will be in the conclusion part I will be explaining what does this condition suggest. Okay, you can draw out some conclusions about the system. Okay, we'll come to that later. Now how to find out s raised to 0? So you need to get the auxiliary equation for finding out s raised to 0. Now look at this. To find out s raised to 0, first of all what you need to do is look at the row just above the all rows, 0 rows. Okay, so in this case s raised to 1 becomes all the elements of s raised to 1 becomes 0. So look at this, look at the row just above that, that is s square. Now you can write an equation corresponding to that. So the equation corresponding to s square row is 2s square, right? And this will be the term corresponding to n minus 1. So it will be n minus 2, right? This is n, this is n minus 2. So in that case, this is s square. That is, this corresponds to 2s square, right? 2s square. Then this will be s raised to 0, which is, this is called as an auxiliary equation, and you will call this as a of s, right? So now what you need to find out is, you need to take the derivative of this. Take the derivative with respect to s. Now how will you find out the derivative? So this will become 4s plus 8 plus 0, right? 4s plus 0. So it becomes 4s. That means now you can rewrite this s raised to 1. Again, I'm following the rest. Okay. You can leave the space for this, right? While you do, you may combine all these together. You can show this these steps. You don't need to show the steps in between this array. Okay. So be careful about that when you do in your exams and so on. Do this as a continuous thing, and when you have this, so you may do each step by step. Don't write s raised to 0 and 0. So if such a thing happens, find out then again rewrite that s raised to 1. Now what will be the s raised to 1 now? Now the new element will be 4, next is 0, next is 0. Okay. Now what you need to combine is, you need to combine, I'm just writing it again for you, s square, which is 2, 8 and 0. So what will be the next step? Next step will be, right, 8 into 4, 32, 32 minus 0, that is 32 by 4, which is 32 by 4, which is actually you are going to get this as 4, right? Right? So this will be 4, 0 and 0. Now look at this first column. When you look at the first column, there is no sign change, no sign change, no sign change, no sign change. And this is the problem. Here, you must be very careful in the conclusion. As far as your knowledge right now, you may say that this system is a stable system. Why? Because the number of positive number of positive right half poles is equal to 0. Why you believe that? Because there are no sign changes is equal to 0. But that is a problem. Now let us try to solve this auxiliary equation. Now solving this auxiliary equation is a part of this polynomial. That means when you solve, the roots that you get is also valid for this polynomial as well. So right, if you equate this to 0, this 2s square plus 8 is a factor of this characteristic polynomial. What happens when you equate this? When you equate this becomes 2s square minus is equal to minus 8, s square is equal to minus 4, right? Now s is equal to root of minus 4, or this is equal to plus or minus j2, right? What is the meaning of that? Now when you plot the poles, you can see that a pole resides at j2 and at minus j2 on the imaginary axis. Now what is this condition called? This is not a stable system. That's why I told you it is not going to be an absolutely stable system. This can be a marginally stable system. So when you solve this auxiliary equation, you can see that there are poles lying on the imaginary axis. That is not a stable condition, that we call as the marginally stable system. So in that context, you cannot call such a system as an absolutely stable system. It is a marginally stable system. And not only that, auxiliary equation gives you an information that the roots lie on the imaginary axis. Okay, so the number of, and that roots can be found out by what? By solving that by that auxiliary equation, you will get the roots. Okay, hope you understood this. Okay, now following can be the conclusions of case 2 which we have studied. Now in this problem which we just did, this is the case, right? We have found out that a pair of conjugate poles lies on the imaginary axis, right? Now another possibility is there can be a situation where there are a pair of roots lying on the real axis but equal in magnitude, but they differ in the sign. That is, one among the roots will be on the right half. So this is one of the case. So this is symmetric with respect to origin, right? With respect to origin, it is symmetric. So that means this much distance is the same as this distance, right? Now another case can be, you can have a pair of complex conjugate roots. That is, say for example, this is 2, for example, j1. Imagine that this is 2 and this is 1. You will call this as 2 plus j1. This is 2 minus j1. So what will be this? Assume that this is 1. So this will be, this is not 2 minus j1. This is 2 minus j1. This is minus, sorry. Okay. So this is the real term. This is 1 and this is 2. You can say that this will be minus 1. Minus 1 plus 2j. This will be plus 1 plus 2j. This will be, this is also 2. So this will be plus 1 minus 2j. This is also minus 1 minus 2j. Okay, so you can have such a scenario as well. So in such a scenario also you will arrive at this condition. Okay, so this case can denote any one of these conditions. Okay, so you'll be getting that information by solving the auxiliary equation. Now in this problem, when you solve the auxiliary equation, you have seen that the poles lie on the imaginary axis, and that is the second case as I have shown here. Okay, right? A few more important points you need to understand. Now from this problem, this is a problem where all elements in a row is 0. We have found out that. And the auxiliary equation, when we wrote the polynomial, so that's an even polynomial. And we have seen that such even polynomial will not be having any right half poles, but it will be having some poles on the imaginary axis. So that's why I told you that this is not an absolutely stable system, because this is on the imaginary axis. And this imaginary axis, once it is imaginary axis, you can say that the response is going to be oscillatory, which we have already studied, right? Because an marginally stable system, we have seen that this is actually the graph of a marginally stable system that is oscillatory in nature. And how will you find out that oscillation? There must be a frequency for there must be a period, and the inverse of that period is going to be the frequency. Now how will you find out that frequency? What is this J2? J2 corresponds to, it is actually J omega, or this is your natural frequency, or this is actually 2 radians per second in this example, right? So this is your omega, right? J omega. So omega is equal to 2 stands for the 2 radians per second, or it is at this frequency this particular system will oscillate. So this is oscillatory in nature. The response is oscillatory with the oscillation of 2 radians per second in this example. Okay.